Welcome to the Crazy Hat Chemist. So today we're doing another video in atomic structure and electron configurations. I can't wait. Bam! So today we're talking about Schrödinger's model of atoms using quantum or wave mechanics. So let's find out the details about this, because it's really stepping on the shoulders of many giants that have already made models for the atom and further refined it. But Schrödinger truly came up with the model. So, Schrödinger applied the idea of electrons behaving as a wave to the atom and used complex mathematical equations. It's calculus-based, in other words, and the development of the wave equation. Okay? The electron in an atom is best described as a standing wave. So I'm hoping you remember back to that standing wave. There is 2 points at the end and at the beginning of that string, kind of like a violin string, if you will. And those are nodes, okay? And you can only pluck at certain sections of this to make the correct note. Therefore, only specific wave functions are allowed with a standing wave, n and half of lambdas. So remember that. Okay, each wave function, psi, is associated with an e sub n, that is the energy of the electron. This introduces quantization naturally, unlike the Bohr model, which it did it unnaturally, where there are only certain, in this model, there are only certain allowable values for the electron in their space. The wave function squared, that is psi squared, is the probability of finding an electron in a three-dimensional region in space, and that is defined as the electron density. We can actually do electron density maps experimentally to prove this model. The equation defines the energy of the electron precisely. I'm hoping that you remember back to Max Born. Okay? And therefore, the solution is the probability of finding an electron in a three-dimensional region or space. This probability is labeled as an atomic orbital. That's not an orbit, but an atomic orbital. I know the names sound very similar, but they are vastly different. An orbit is using Bohr's model, and an orbital is a three-dimensional region in space. An orbital, the probability of finding an electron is defined by a set of 3 integer numbers, or quantum numbers. These quantum numbers are n, l, and m sub l. Okay, this is again all coming from published material in primary resources in journal articles that are read by many different people, okay, and before you publish them, they have to be reviewed. After they're published, they're reviewed, and then they're repeated over and over again from multiple scientists. So this is very important. Then, after multiple reviews, then it finally gets incorporated into textbooks, of which you can learn about. Okay? Electrons are not orbiting the nucleus as in Bohr's model, like the planets do the sun. That does not happen. But the electrons are found in an atomic orbital, that is a three-dimensional region around the nucleus where there is a high probability of finding the electron. If there's a 0% probability, then that electron has been removed and you have an ion. Quantum or wave mechanics uses 4 different quantum numbers to describe the electron in an atom. The first 3, that is n, l, m sub l, describe the atomic orbital. The 4th quantum number, m sub s, is used to designate the magnetic property of electrons, and that is called the spin. Okay? I hope you enjoyed that video, and I got another awesome hat here for you. Yes, indeed. If you like that video, give me a thumbs up. Please subscribe to my YouTube channel. I would greatly appreciate that. Thank you very much.